Hello friends, today we are going to cover our next topic, industrial production, utilization and estimation of our phytoconstant Disgenin. So, today we are going to cover the phytoconstant Disgenin in this class. Disgenin is a triterpenoid saponin. If you look at the structure, you can see the cholesterol nucleus or the cyclopentanophenothrin ring system. Cyclopentanophenothrin ring. So, this cyclopentanophenothrin ring is the basis for various steroidal compounds. So, it makes this nucleus makes the compound a saponin glycoside. So, it is a triterpenoidal saponin glycoside which is isolated from the dried tubers of Dioscorea deltoidea, and the plant belongs to family Dioscoreaceae. This Dioscoreaceae family is especially for such tuberous roots. In Hindi, this Dioscorea deltoidea is also termed as yam. In English, it is termed as yam. It's a white to off-white crystalline powder. And if you look at chemical structure, you can see it is a 3-beta sterol or a spiroketal. As far as the geographical distribution of this particular Disgenin phytoconstant is concerned, it is distributed throughout the world, especially in North America, Japan, China, Mexico, India and Nepal. In Indian subcontinent, the plant grows wildly in the western Himalayas, in Karnataka, Kashmir and West Bengal, or there are other parts of the country India also where this plant is found wild in the forests. Since we are concerned about the phytochemical isolation, so we should know in which solvent this phytoconstant is going to be extracted out. So, here you can see that the compound Disgenin, it is soluble in organic acids and acetic acid. So, we have to use these acids or organic acids for isolation of this particular phytoconstant Disgenin. As far as the uses of this phytoconstant Disgenin are concerned, it is mainly used as a precursor for the steroidal synthesis of various hormonal preparations, and due to this medicinal value, this excellent medicinal value, this plant is widely cultivated throughout the world. Especially this phytoconstant Disgenin is utilized on a large scale, and it is cultivated on a large scale for the preparation of ever increasing demand for hormonal preparation throughout the world. Moving on to the next slide, if you look at the cultivation of Dioscorea deltoidea, you can see these are the fields where the Dioscorea is cultivated, and it requires because it's a creeper, it requires a support to climb, it's a climber, it requires a support to grow, and because we are using the tubers or the dried rhizomes, this plant requires excellent growth. So, when this aerial part grows too much, only then this tuberous roots it is generated in the plant. So, these are the cultivated fields of Dioscorea plantation, and if you look at the plant, this is the tuberous part of the plant which we utilized for isolation of Disgenin phytoconstant, and this is the aerial part which generally we do not require, and nowadays research are being made on isolation of phytoconstant from the aerial parts also. This is the dried powder of our phytoconstant Disgenin. So, in this way we cultivate the Dioscorea on a large scale in the fields. If we look at the mechanism of action, because we are studying the phytochemical individually, so we should know how this phytochemical is going to act on your body. It has got a tremendous activity in your body. If you look into the picture, you can see that it helps, or it has its role in eicosanoid biosynthesis. It helps its action in inflammation. So in this way it is acting as anti-inflammatory. The compound Diosgenin is acting as anti-inflammatory. It helps in homeostasis or management of calcium inside your body. It also helps in the biosynthesis and metabolism of protein in your body. It also helps in metabolism of fatty acids in your body. It also has its role and its involvement in cell proliferation and growth, and due to this activity, this Diosgenin is especially used for preparation of your hormonal preparations. It also induces apoptosis, and if something induces apoptosis, which is a programmed cell death, in this way it also acts as anti-cancer drug. And because Diosgenin is involved in the protein synthesis regulation, so it also shows the antiviral activity, because in in virus replication proteins are involved. So in this way it has got various uses like anti-inflammatory action, calcium homeostasis management, protein biosynthesis and metabolism, fatty acid metabolism, cell proliferation and growth, as anti-cancer and antiviral drug. So these are the mechanism of action, the uses of this phytoconstituent Diosgenin in your body. If we move to the extraction method, there are two extraction method we are going to discuss. Since the phytoconstituent Diosgenin is soluble in organic acids and acetic acid, so we have involvement of acids and organic acids in the extraction part. So in this this is the alcohol extraction method. Here what we do, we took the dried tuberous roots, and the powder of dried tuberous roots, it is extracted with 90% ethanol for 2 times for a time period of around 6 to 8 hours using Soxhlet apparatus. The functioning of Soxhlet apparatus we have seen in previous lectures. So after 6 to 8 hours of Soxhlation, the mixture is filtered. The filtrate thus obtained is that it is concentrated under vacuum to a syrupy liquid. So we use the rotary vacuum evaporator for concentration of this extract. The syrupy extract is then subjected to acid hydrolysis. Acid hydrolysis using dilute HCl or sulfuric acid. So here we use dilute hydrochloric acid or dilute sulfuric acid, and the mixture is left aside for 2 to 8 hours. After 2 to 8 hours of left aside, you will observe that around 85% of the Diosgenin which was present in the extract, it gets precipitated, and this precipitate is then again washed with water, because Diosgenin is soluble in organic acids and acetic acid, but it is insoluble in water. So you can use the water for washing of this precipitate of Diosgenin, and after washing you can see the water soluble impurities, they can be easily removed from your Diosgenin, and this is the crude Diosgenin which can further be purified using alcohol. So this is the alcohol extraction method or alcohol isolation method which we can use. Next we have acid hydrolysis method. In this method what we do, we took the dried tuberous powder of the Dioscorea, and we reflux it for about 2 to 6 hours using 2 to 4 normal mineral acids in autoclave. I like to show you the autoclave. This is the reflux. This is the reflux we use here. what happens in the reflux? We take the drug and the solvent. We take the drug and the solvent in the round bottom flask. We apply heat, and due to the application of heat, both drug and solvent they boil together, and the the vapors of solvent they evaporates, and due to the cold water inlet, at the condenser, the vapors they get condensed into water droplets, and again the drops they attach to the condenser wall, and they came back again to the reservoir. This is the reflux condenser we use in this acid hydrolysis method. Going to the back, after this acid hydrolysis with the reflux, the mixture is then filtered. The mixture that we obtained after refluxing, it is then filtered, and the murk is the drug which is collected on the filter paper. The murk is then washed with water till it become neutral. So you have to wash the murk until it become neutral. The neutralized murk which we have obtained on the filter paper, it is then dried, and it is extracted with hydrocarbon solvent. You can utilize any hydrocarbon solvent. It can be ethyl acetate, it can be methanol, it can be ethanol, and after the extraction, the extract is then filtered, and the filtrate is subjected to vacuum evaporation and concentrated to a syrupy liquid. It is about 25 ml, and this concentrated extract or liquid, it is then refrigerated for about 1 hour. After refrigeration for 1 hour, you can see the formation of crystals of Diosgenin inside your concentrated extract, which are then again purified using acetone. So this is the acid hydrolysis method we can utilize for production of Diosgenin. Moving on to the chemical identification test of Diosgenin, we can take the sample. We add acetic anhydride to the sample, and the mixture is then heated. After heating, the mixture is cooled, and the mixture is treated with concentrated sulfuric acid slowly, which is added to through the side tubes, and if there is a formation of green color, then it confirms the presence of Diosgenin in your sample. Diosgenin in your sample. This is the reflux we have used. And this is the assembly of Soxhlet, which we have already discussed in our previous lecture. What happened here in the Soxhlet apparatus? Here is the heat source. We applied the heat. Solvent vapors they get evaporated. And they enters the extractor where we have drug packed in the form of thimble. The solvent vapors they try to escape through the condenser, because there is a cold water inlet at this place, so they stick to the condenser wall, and after some time they get condensed, and after condensing they fall freely on this your thimble, which is packed with the drug. And this association of drug with the solvent, it causes the extraction of phytoconstituent into the solvent. So this solvent, as soon as it reaches this height, the height of siphon tube, this is siphon tube, as soon as the solvent level in the extractor it reaches this height, the siphoning starts. The liquid which is filled up over here, it goes back to the main reservoir. In this way, again and again several cycles of siphoning they takes place, and your phytoconstituent it get extracted in the solvent properly. This is the separating funnel we have already discussed in our previous lecture. Here the separation of two immiscible liquids takes place. The separation takes place naturally, but we can also partition the phytoconstituent from one solvent to another on the basis of its solubility and its partition coefficient between various solvent systems. This is the rotary vacuum evaporator, where we have the involvement of rotation, vacuum and evaporation. rotation of this round bottom flask, heat is applied. What happened? The filtrate which is put over here, it forms a thin film on this surface, and this film, the molecules get evaporated at a very low temperature. Solvent vaporizes at low temperature due to formation of thin film. Okay. Simultaneously, we also apply vacuum through this vacuum pump, and due to this our solvent vapors our solvent get vaporized at a very low temperature, preserving the thermolabile phytochemical in the filtrate. So, in this way you can recover the solvent also, you can recover the solvent. The advantage of this technique is solvent recovery. And protection of your phytoconstituent. Phytoconstituent, which are generally thermolabile. So, in this way you can use the rotary vacuum evaporator for efficient extraction and efficient isolation of phytoconstituent without damaging the integrity of the phytoconstituent. Moving on to the next slide, here are the properties of Diosgenin. Diosgenin has got a melting point of about 205.5 degrees centigrade. Boiling point of Diosgenin is about 527.11 degrees centigrade. Solubility, we have seen the solubility on the very first slide also. It is soluble in organic solvents and acetic acid, but it is insoluble in water. Density of Diosgenin is about 1.0984. The storage temperature for pure Diosgenin is -20 degrees Celsius, and it occurs in the form of white to white crystalline white powder, which can be in the form of crystals or in the form of powder, depending upon the method of extraction. So, the water solubility, as we have seen that it is poorly soluble in water. So, you can see here that only 0.02 mg 0.02 mg of Diosgenin is can be solubilized in 1 liter of water. The lambda max for Diosgenin is about 205 nanometer. It means that Diosgenin shows maximum absorbance of UV radiations at a wavelength of 205 nanometers. Moving on to the analysis part or the estimation part, here we use thin layer chromatography and the high pressure liquid chromatography. You can see the TLC specifications we have used for here we have used silica gel, which acts as a stationary phase. So, these are the pre-coated silica gel plates we have used for separation of our phytoconstituent Diosgenin. These silica gel plates, they are spotted with the drug or with the standard, and the mobile phase we have used for thin layer chromatography are N-heptane and ethyl acetate in a ratio of 7:3 volume by volume. Under these conditions of your mobile phases and your stationary phase, you can get the RF retention factor value for Diosgenin in the form of green spot at an RF value of 0.47, and this green spot is due to derivatization of the plate using glycyl acetic acid and methanol in a combination of 85:15 and anisaldehyde in a ratio of 1:1. Means this solvent 1 part and this anisaldehyde 1 part, together this will form the derivatizing reagent, and this reagent is sprayed on your thin layer chromatography or thin layer your plate TLC plate, and after spraying you can observe the green spot of Diosgenin at an RF value of 0.47. The sample for this analysis was prepared by dissolving 1 mg of your drug, which is supposed to contain Diosgenin, in 50 ml of chloroform, because the compound is soluble in chloroform. The standard Diosgenin is dissolved, 1 mg of standard Diosgenin is also dissolved in 10 ml of mobile phase, and in this way we have prepared the test and the standard solutions. For HPLC analysis, for high pressure liquid chromatography, we have used the C18 column. Here C18 column we have used. C18 column is the column in which we have the stationary phase silica gel is the stationary phase, which is coated with a polymer with 18 carbon atom. So, in this way this polar phase is converted into non-polar phase. So, stationary phase is non-polar here, and you can utilize polar mobile phases for efficient analysis or efficient separation of your phytoconstituent. Here in HPLC we have utilized mobile phase methanol water in a combination of 90:10, both are polar solvents, and the your stationary phase is non-polar, and we can have the efficient isolation. The flow rate through the column was the flow rate of the solvent through the column was maintained at 0.4 ml per minute, and a 20 microliter injection was injected into the column for separation. The UV detector of high pressure liquid chromatography or your HPLC instrument was set at 203 nanometers, and under these conditions you get the spot of or the peak of your Diosgenin at retention time of 6.5 minutes. It means that your after the injection of your sample into the column, your compound reaches the detector in 6.5 minutes, and this is the retention time of your Diosgenin in the sample. Retention time varies from method to method. If you change the mobile phase, then retention time varies. If you change the speed of mobile phase or the flow rate of the mobile phase, the retention time changes. So, under above prescribed condition, you get the retention time value at 6.5 minutes. The sample was prepared by dissolving 10 mg of extract in 10 ml of methanol. The mixture is sonicated for 10 minutes and filtered using 0.2 micrometer filter paper or membrane filter and injected into the HPLC. The standard is also prepared. 1 mg per ml 1 mg per ml stock we have prepared, and from that stock we have prepared several dilutions for preparation of calibration curve. So, what happened, you prepare the calibration curve using standard. These are the concentration, and this is the area under curve, and this is the concentration. So, you get a curve, and when you inject your sample you get a value of area under the curve, and on the basis of area under the curve value you can detect the exact quantity of your sample of your drug in the sample. So, this is the HPLC analysis of your Diosgenin in the sample. This is the TLC and HPLC diagram. TLC, this is the spot, green spot of Diosgenin observed at 0.7, and these are the other hydrolysis product which are also present inside your sample. This is the HPLC, this is the HPLC of Diosgenin spectra of HPLC spectra of Diosgenin standard, and this is the Diosgenin in extract. So, there are other peaks also, and if we get the peak at this retention time 6.4 retention time, any peak at this retention time gives you the concentration of your sample in the drug. Moving on to the HPTLC analysis of Diosgenin, we have used the Kamag Linomet applicator, TLC applicator, we have used the Kamag twin trough glass chamber, we have Kamag TLC scanner model and other Kamag WinCat software. So, everything in HPTLC is automated. It is very much similar to the thin layer chromatography which we have studied in the previous slide, but here everything is automated. Sample application is automated, sample visualization is automatic. So, everything is automatic. So, the results can be reproducible. HPTLC analysis has the benefit of reproducibility. The method can be reproduced anywhere in the world using the same condition. Here we have used the pre-coated silica gel plates, HPTLC plates we have used, nitrogen gas we have used for sample application. The mobile phase, here we have used N-hexane and ethyl acetate in a ratio of 75:25, and under these conditions we have performed our HPTLC analysis for Diosgenin. The TLC chamber was saturated for about 10 minutes. The chamber saturation is also automatic. So, there is no chance of error, because most of the things they are being done automatically. The total run time is about 25 minutes at a room temperature of about 27 ± 2 degrees centigrade. Mobile phase run distance is about 8 centimeter from the point of application. Derivatizing reagent we have used is anisaldehyde sulfuric acid reagent, which we have sprayed on the developed plate. After derivatizing the reagent, we have observed the Diosgenin spot on the on our plate. The TLC plate was dried at 105 degrees Celsius using hot air oven. Here everything, drying is also automatic, derivatization is also automatic. You only have to fill the readings into the software, and the software here we have used is Camag Wincats software, Camag Wincats 5 software. Camag is the largest manufacturer of HPTLC instruments throughout the world. They are involved in HPTLC studies of various herbal drugs, and you can say for herbal drug studies or for herbal drug research, HPTLC is the main instrument, or you can say the lifeline of herbal drug research. This is the chromatogram of HPTLC we have obtained in HPTLC. So, it is the peak of Diosgenin in our sample. It shows the concentration on the basis of area under the curve. This area under the curve, this reading is to be mentioned into the calibration plot. Suppose this is a calibration plot, here is the concentration and here is the area under the curve. You have to choose that concentration, and if you interpolate this onto the calibration plot, you get the concentration of your phytoconstituent in your drug sample. So, this is the HPTLC analysis of our phytoconstituent. Moving on to the utilization part of Diosgenin or the uses of Diosgenin. As we have seen in the very first slide, that Diosgenin is being cultivated worldwide because of its high medicinal value. We have got its antiviral action, we have got its anti-cancer action, we have got its anti-inflammatory action, we have got its protein metabolism and hemostasis, calcium hemostasis management uses. So, there are various uses of Diosgenin, but mainly the Diosgenin is used as precursor for commercial synthesis of cortisone, pregnenolone, progesterone and other steroidal products which are available in the market on large scale. It is also employed in the treatment of hypercholesterolemia, high level of cholesterol, inflammation and infection. It is also used as anti-cancer and antiviral drug. So, these are the uses of Diosgenin which we have to study, which we have to remember about Diosgenin. Thank you so much. This is all about Diosgenin. In our future lecture, we will cover our next topic, which is Senocide. Thank you so much.